Welcome geometry to the lesson 4.5 video on isosceles and equilateral triangles. Students will be able to use and apply properties of isosceles and equilateral triangles. So that's lesson 4.5. So 4.4 would be the last of the new types of proofs for now until we get to something special in 4.6. This is not so much about proof. This is more about using congruent angles and congruent sides to decide things. All right, so the first thing it says here is the angles and sides of isosceles triangles have special relationships. So let's define what isosceles triangle means. An isosceles triangle is just a triangle with two congruent legs. So on the one triangle itself, two of the sides have exactly the same length. So what we call the congruent sides legs in an isosceles triangle. There's one more side left, and that third side is called the base. The two congruent legs form something called the vertex angle. It's usually at the top if the base is on the bottom. And then the other two angles are called base angles. All right, so in our picture, the legs are in red because those are the two sides that are congruent to each other. The bottom side is called the base. It's not congruent to anything in this triangle. On that base, you find the base angles, and we're going to get something about that very shortly. The only angle left is called the vertex angle up top. That's not congruent to anything either. All right? The isosceles triangle theorem says this. If two sides of a triangle are congruent, so this part means if you have an isosceles triangle, so in any isosceles triangle, what ends up being true is the angles opposite those sides are congruent. So another way to say that is the base angles are congruent. Okay, so what that means for us is if you see an isosceles triangle, you can say the angles opposite that are congruent. The base angles will have to be congruent if the triangle is isosceles. Okay? Let's look at a proof of that isosceles triangle theorem with what we have so far. So what we know, oops, I scrolled just a tad too much. The proof of this theorem requires an auxiliary line, so that's going to be this line right down the middle. We're drawing that line so that it bisects the vertex angle up top. So what we know is that xy is congruent to yz, making the entire triangle, the whole thing, isosceles. We want to be able to say why that means that the triangles are, or that the angles y and z are the same. Okay? So one step that we have, this auxiliary line that we can draw in, is congruent to itself, meaning we can use the reflexive property like we've done 100 times. XB has to be congruent to itself. We can also say angle 1 and angle 2 are congruent because we made it that way on purpose. We made the red auxiliary line an angle bisector. So in this situation, we have enough to say the triangles are congruent by side, angle, side. In both of these triangles, we have two pairs of sides congruent, the ones that were given, and then the auxiliary line, and then we have the angle in between. So we can do a step to say side, angle, side says the triangles are the same. And what you learned in section 4.4 is if those are congruent, that means that any corresponding parts of the triangles have to be congruent. And since y and z go together, they have to be congruent by corresponding parts of congruent triangles being congruent, CP, CTC. So that's a proof of why in any isosceles triangle, the base angles have to be congruent, just so you'll have two pairs of angles congruent, just like you would have two pairs of sides congruent. All right, moving on to some more examples with that. So this does have a converse before I get too far. It does have a converse. This one's going to say if the base angles are congruent, then the sides opposite are congruent. So it's saying if you see the two base angles congruent, that means it has to be an isosceles triangle. Okay? Isosceles triangles will have two congruent base angles and two congruent sides. It doesn't matter which one you see first. Okay? So in that manner, if I see on number 10 right here that these two angles are congruent, that means these two are the base angles. All right? If the base angles are congruent, that means that this is an isosceles triangle, which means 11 has to be equal to x plus 4. In this case, 11 is equal to x plus 4. When I subtract both sides by 4, x is 7. And this, all I'm doing right here is solving for x. Okay? Same thing here. These base angles being congruent mean the two legs have to be congruent, meaning 12 has to equal 6x, or x has to equal 2. All right, and this one solves pretty quickly. Here's my base angles. If I go across to the other sides, the legs have to be congruent, which means x has to equal 13, and that one is already solved. Okay? Pause the video right now and do those bottom three. When you're done, resume the video and check your work. All right, so here's your answers to 13 and 14. We have our base angles being congruent, which makes the sides opposite congruent. When you set 7x plus 5 equal to 19, you get an answer of 2. Hopefully you got that one right. This one's going backwards. We know the sides are congruent. That means the angles opposite have to be congruent. So 5x plus 7 equaling 52, which gives us an answer of 9. And then we're at 15. A little bit of a trick question here. But what we have is 4x, which is not on the base. This is a vertex angle. The base angles are 3x and this angle here. So what we have this time is not a situation where 3x equals 4x, because this time the two angles that are equal are the base angles here. So what we can do to get around this, maybe we could say if there's a 3x in this corner, we could put a 3x in that corner, and now we can use 180 to solve for this one. Since they gave us a vertex angle, we need to do it a different way. So we could do that there's two 3x's and then a 4x that all make 180. That would be a way that we could do this problem. 3 plus 3 plus 4 would give us 10x equal to 180. When we divide that by 10, it looks like x is supposed to be 18. We could plug that back in and everything should make 180 when we're done. Okay, so that's how you might use the isosceles triangle theorem or its converse to solve for missing sides or missing angles. Okay, and right here we have a theorem for 5, which is just going to help us out with a couple things here, or a couple problems that we might see. It says if a line bisects the vertex angle of an isosceles triangle, so if it cuts that top angle in half, that line is also the perpendicular bisector of the base. What that means is if you see a line that cuts the top angle into two congruent pieces, that means that that line will be a perpendicular bisector, which means that I'm going to draw that a little bit larger. That triangle, if it's isosceles, the line right down the middle will not only cut the top part in half, it'll also cut the bottom in half at 90 degrees. That's theorem 4-5. An application of that would be right here where it says, what is the value of x? Okay, this 54 is talking about this angle right here. Okay, they're saying the value of x right here is this angle that's missing. All right, but since I see that this is an isosceles triangle, and I see that this line down the middle, BD, is cutting this in half, that means I can say that this is definitely a right angle right here. This is a perpendicular bisector. Okay, which means for me, first off, since it's isosceles, if it's 54 in this top corner, I could put a 54 down here. And now I just have a 180 problem. X plus 54 plus 90 is going to be equal to 180. And that's something that I can solve for x by just subtracting 144 from 180. Okay? That's just a theorem. You don't have to know it by name. It's just 4-5, but it's something that you might use. All right, last idea is bringing equilateral into the mix. All right, equilateral triangles are just a special case of isosceles triangles. So just a couple definitions here right away. When I say equilateral triangle, that means all three sides are the same. Equilateral is going to also mean that the angles are all the same. So equilateral is talking about all three sides being the same. All equilateral triangles have three congruent angles as well, which is always the same thing, 180 divided by 3. Sometimes you might hear them called 60, 60, 60 triangles. Okay? This one is kind of a converse. If you see an equiangular triangle, if you see a 60, 60, 60, that means the sides have to all be the same. So if you have 3 60s inside of a triangle, or they're all marked to be the same, that means that it has to be an equilateral triangle. So let's solve a couple practice problems with equilateral and see what we can come up with. All right? So these are two separate problems. The one with the picture on the left is separate. Let's look at this one first. We see that it's equilateral, which means it's equiangular, which means every angle has to equal 60. So to solve something like this, we could set 2x plus 10 equal to 60, which makes 2x equal to 50, or x equal to 25. Okay. This one says the measures of two of the sides of an equilateral triangle, two of the sides of an equilateral triangle are 3x plus 15 and 7x minus 5. We want the measure of the third side in inches. So if I were to draw a picture of this one, two of the three that are all the same are 7x minus 5 and 3x plus 15. What I know about the sides of this triangle is that they are all congruent to each other, which means I can find x by setting these two equal to each other. So if I subtract both sides by 3x and add 5 to both sides, I get 4x equal to 20, or x equal to 5, which is part of the answer. They want this third side, which is going to be the same length as either of the other two. So I can plug that 5 into one of these. Say I do the 3 times 5 plus 15. I would get 15 plus 15, or 30. This side has to be 30. Okay? So equilateral triangles, you can use the fact that all the sides are the same to your benefit. You can also use the fact that all three angles are 60. Okay? All right, last two here. What I know right now is that if this is equilateral, then all these angles are 60s. So I could set 4x equal to 60 to find x. When you divide by 4, x has to be 15. And I can also use linear pairs or exterior angle theorem. Y plus 60 has to equal 180 since that's a linear pair, or y has to be 120. Okay. Last one here is a combination of different types of triangles. The triangle that I'll make blue right here is an isosceles triangle. The triangle here that I'll make green is going to be isosceles as well. It's just that we have two of them. So that means that whatever m is, this is the same, and whatever n is, this is the same here. All right? So this one on the right is called a right isosceles triangle, this blue one. I know that this means 90. So I know that n is both of these corners. I could do n plus 90 equal to 180, or 2n plus 90 equals 180, which would mean that I could say 2n equals 90, or n has to be 45 in this situation. And in this problem, n being 45 is helpful. Since there's one arc on this one, that means I can put a 45 up here and do the same type of situation. These two m's have to be the same. I can do m plus 45 equals 180, or 2m plus 45 equals 180. and then solving that gives you the answer of 67.5. Thanks for watching.